Welcome to the 10 popular coding interview problems course. 10 well-chosen problems that cover different algorithms and data structures topics to increase your knowledge and prepare for interviews. Please try to solve before watching the solution. Prepare yourself and see you in the first lecture. Welcome to this video where we will solve the first problem of this course, valid anagram, a quite easy problem compared to next ones. We are given two strings s1 and s2 and we are asked to check if they're anagrams. Two strings are anagrams if they're made of the same characters with the same frequency, just in a different order. For example, with the strings danger and garden, we take one of them, we rearrange its characters, and we get the other one. How are we gonna solve this problem? We know that two strings are anagrams if they have the same characters with the same frequency. So what we can do is to calculate the frequency of each character in S1, calculate the frequency of each character in S2, and compare the results. But what structure do we use to do so? We can use an array where each cell represents the number of frequencies. They all start at 0, then for each character in the string, we increment the corresponding cell. This solution is suitable when the alphabet is small, when the number of possible characters is not big. For example, if the strings can only be made of lowercase alphabetical letters, we'd need an array of 26 elements, it's fine. But it's not necessarily the case. They can contain all the characters. And we have thousands and thousands of existing possible characters. The array would take a lot of time and space to create it and traverse it. The best structure for our problem is the hash table, a structure that maps unique keys to values. In our case, the key will be the character and the value's number of occurrences. For example, if we have nameless and salesman, with nameless we get this hash table, and with salesman we get this one. Here they have the same keys with the same values, so they're equal. It means that nameless and salesman are anagrams. In code, we first check that both strings have the same length, because if they're not, it's impossible for them to be anagrams. Then, we create our two hash tables and we start traversing. For each character in S1, if the key is already existing in frag1, we just increment, else we create it and we set its value to 1. Then for S2, same logic but with frag2. Now that we filled them, we check that they have the same values. For each key in frag1, if it doesn't exist in frag2 or frag1 of key isn't equal to frag2 of key, we return false. It means that either the character of S1 doesn't exist in S2 or they don't appear the same number of times. After the loop, if we didn't find any difference, we return true. And in Python, we don't even need to write all of this because we have a class named counterInCollections module that builds the table of occurrences just by passing the string as an argument. And we can compare dictionaries with the equality operator, so in reality, we just return counter of S1 equal to counter of S2. For the time complexity, in the worst case, S1 and S2 have the same length, let's name it n. We're traversing n characters at most 3 times, and searching and inserting in a hash table costs O of 1 in average. We get O of n plus O of n plus O of n, which gives an O of n time complexity. And for the space complexity, we have O of n for each table because they can contain up to n keys each. We get an O of n space complexity. We still have another solution to discuss. You have to know that two anagrams have the same lexicographically sorted string. For example, with nameless and salesman, if we sort nameless, we get AEELMNSS, and with salesman, same thing. So in the second solution, we just sort both strings and compare the results. In code, after the equal length condition, we return sorted S1 is equal to sorted S2. That's it. Sorting a string of n characters costs O of n log n time, we're doing it twice, plus n for comparing, we get an O of n log n time complexity. And for the space complexity, we have O of n for the sorted result, twice, we get an O of n space complexity. We reached the end of this video, we solved the valid anagram problem. I hope that you understood both solutions, and see you in the next one. Welcome back to the course. In this lecture, we will solve the first and last position problem. We are given a sorted array of integers r and an integer target, and we are asked to find the index of the first and last position of target in r. If target can't be found in r, return -1, -1. For example, if r is 2, 4, 5, 5, 5, 5, 5, 7, 9, 9, and target is 5, the output would be 2, 6. Because the first position of target is 2 and its last position is 6. First of all, because the array is sorted, all the elements with the same value will be adjacent to each other. For example, here all positions of the value 5 are consecutive. It means that the first possible solution is to start traversing the array from the beginning, find the first position of target, and keep walking until finding the last position. With our example, we have 2, 4, then 5, we found the first position. We keep walking, we have 5, 5, 5, 5, this one is the last one. We found the end position, we return them. In code, we start traversing indexes of r, and if r of I is equal to target, it means that we found the start position. Now we keep walking while the next element exists and is equal to target. While I plus 1 is smaller than length of r and r of I plus 1 is equal to target, we increment I. After the while loop, I now represents the position of the last occurrence. This is why we return start I. And if the for loop ends without having returned the result, it means that we didn't find target in r at all. We return -1, -1. Note that it's possible to have start position equal to end position. It happens when there is only one occurrence of target in R. For the time complexity, when target exists, we traverse the path before its first position, then its sequence of occurrences, and when it doesn't, we traverse the whole array. In both cases, we traverse at most n elements, where n is the number of elements of R. We get a time complexity of O of n. And a constant space complexity because we're just using int variables. This solution uses linear search, which gave an O of n time complexity. But the array is sorted, so we can think of using binary search. Let's try to use binary search to find the start position. With binary search, we can find the position of an element in a sorted array, but here we're not searching for any position of target, we're searching for the first one. I is the first position of target if r of I is equal to target, obviously, but also r of I minus 1 has to be smaller than target, smaller because the array is sorted. So we will use binary search normally, but we add the second condition before returning mid. Let's try it with our example. Left and right start at first and last element of r as usual. Mid is left plus right divided by 2, we get 4 here. It's true that r of 4 is equal to target, but it's not enough. R of 4 minus 1 is not smaller than target, so mid is not the starting position of target. But should we go to the left part or to the right part now? R of mid is not greater than target, so the first position can only be in the left part. We continue. Mid is now 0 plus 3 divided by 2, we get 1. R of 1 is smaller than target, so the starting position can only be in the right part. We continue. Mid is now 2 plus 3 divided by 2, which is 2. R of mid is equal to target, and R of mid minus 1 is smaller than target, so mid represents the first position of target, we return it. In code, we can first have an early exit condition for the case where the first element is equal to target. We directly know that 0 is the starting position, we return 0. By the way, in solutions based on binary search, put as much early exit conditions as possible to handle edge cases and avoid out-of-bounds problems. After it, we initialize left and right at 0 and n-1 respectively. 0 and n-1 are the indexes of the first and last element of R. Now while left is smaller than or equal to right, we calculate mid-index. It's left plus right divided by 2. After it, we have 3 cases. The case where both conditions are respected, where r of mid is equal to target and r of mid minus 1 is smaller than target. It means that mid is the starting position, we return it. Second case, r of mid is smaller than target. It means that we're still before the starting position. This is why we take left to mid plus 1, to start again in the right part. Else, it means that we exceeded the consecutive sequence, or we're inside it but not at the beginning. so start can only be in the left part, we take right to mid minus 1. And if the while loop didn't return a result, it means the target doesn't even exist in R, we return minus 1. Now we found the start index, but we still need to find the end index. We can think of just walking starting from start until we find the last position of target. But it would ruin everything we did, because in the worst case, we need to traverse the whole array, which results in an O of n time complexity, same as the first solution. You guessed it, to find the end index, we will also use binary search. But the condition is a bit different from the first time. When searching for the start position, R of mid had to be equal to target and R of mid minus 1 smaller than target. And for the end position, R of mid has to be equal to target and R of mid plus 1 has to be greater than target. Next element has to be greater because it would mean that from the right, we're not in consecutive target elements anymore, so the actual position is the last position of target. In code, we just change a few things. The early exit condition occurs now when the last element is equal to target. It means that the last position of target is in the last index of R and minus 1 without clear return. Then in the three cases, the cases where we return mid is when R of mid is equal to target and R of mid plus 1 is greater than target. For the two remaining ones, here when R of mid is greater than target, then we exceeded the consecutive sequence. We go to the left part, right becomes mid minus 1. Else, it means that either we're before the consecutive sequence, or we're inside it but not at the end, so end can only be in the right part, left becomes mid plus 1. Now we have our find start function, we have our find end function, we can move to the main solution function. First of all, we have some early exit conditions. We can identify at least three cases where we can't find target at all, when the array has no elements, when target is smaller than the first element, and when target is greater than the last element. In the last two ones, because the array is sorted, we can deduce that target is not equal to all other elements. If at least one of these conditions is true, we directly return minus 1 minus 1. Else, we call find start to get the start position, we call find end to find the end position, and we return start end. If target doesn't exist in R, start and end will have returned minus 1 both. We still get the expected result. For the time complexity, we're using binary search twice, and binary search has an overlog n time complexity because we keep dividing the input size by 2. 2 times overlog n gives an overlog n time complexity. And for the space complexity, we got O of 1 because we're just using int variables. Before ending this lecture, I want to tell you that if you're not comfortable with binary search, you should really work on it because it's a fundamental algorithm technique that appears in many problems, like this one, find peak, first bad version, and many other ones. We reached the end of this lecture. I hope that you understood the solutions, and see you in the next one. Welcome back to the course. In this lecture, we will solve the kth largest element problem. We are given an array of integers and an integer k, and we are asked to find the kth largest element. For example, if we have r equal to 4, 2, 9, 7, 5, 6, 7, 1, 3, and k equal to 4, the output should be 6, because the largest element is 9, the second largest is 7, the third largest is 7, and the fourth largest is 6. A first possible solution that we may think of is to remove the maximum element k minus 1 times, because after doing so, the next maximum represents the kth largest element. For example, with our array, k is 4, so we remove the maximum element 3 times. First iteration, max is 9, we remove it. Second iteration, max is 7, we remove it. Third iteration, max is 7, we remove it. Now that we finished the 3 iterations, the maximum in the remaining elements is the kth largest element of the original array. It's 6 here. We return it. In code, we have a for loop that is repeated k minus 1 times where we remove the maximum element. After the loop, we return max of r. That's it. For the time complexity, searching for the maximum costs O of n, where n is the number of elements, and removing it from the array costs n in the worst case, because we may need to shift all the n-1 elements. And our loop is repeated k-1 times. We have k-1 times 2n, plus n for finding the final largest element. In total, we have k-1 times 2n plus n, which is 2 times k times n minus n, which gives an O of k times n time complexity, where n is the number of elements of R. I know that in reality, during the iterations, n will decrease because we have less and less elements, but we get the same time complexity. And for the space complexity, we're not using input size related variables, we have a constant space complexity. This solution is a bit slow, let's move to the next one. The idea of the second solution is to start by sorting the array, because by doing so, we know that the largest element is at the last cell, the second largest element just before it, the third largest just before it, and so on. With our array, we sort it, and k is 4, so we return the fourth element starting from the end. In a general way, we sort R and we return R of n minus k. N minus k represents the index of the kth element starting from the end. For the time complexity, we have O of n log n for sorting the array and O of 1 for accessing. We get an O of n log n time complexity. And for the space complexity, it depends on the space complexity of the sorting function. This solution is way faster than the first one, except in some cases, but we still have another solution to discover. In the first solution, we didn't have to sort, which is good, but searching for the maximum costs n at each iteration, which slows down the process. What if instead of n, getting the maximum cost log n only? Yes, it's possible by using a priority queue. A priority queue is a queue where the next element to be popped is not the first one that entered, but the one with the highest priority, and it's usually implemented with a heap. If you don't know about heaps and priority queues, you should really watch my YouTube video on the subject. You'll find the link below, or you can just search for inside code heaps on YouTube. And after building our priority queue, popping the next element costs O of log n only, so we just have to pair the cost of building the priority queue, which is n. For example, with our array, this is what our heap would look like. You can see that the element at the top is the greatest one. We extract it, and it costs O of log n to rearrange nodes. Second iteration, we extract the root, and it costs O of log n to rearrange, to maintain the order. Third iteration, same thing. Now that we did the k-1 iterations, the next extracted node is the kth largest element, we return it, here it's 6. In Python, we have the heap queue module, but the problem is that it's implemented with a min heap, not a max heap, so at the top we will find the smallest element, not the greatest. To counter that, we just multiply values by -1 to reverse the order. So we start by replacing R by -lm for each element in R. After doing so, we heapify R to make it respect the heap property. And now we're ready to start extracting. We extract from it k-1 times. After the loop, we extract the last time and we return the result multiplied by -1 obviously to get the original number that was in R. For the time complexity, we have n to build a new array with reversed values, n to heapify it, go check the video to know why, and then we have k-1 iterations. Each iteration costs O of log n to extract. After the loop, we have O of log n to extract one more time. In total, we have 2n plus k-1 times log n plus log n, which is 2n plus k log n, which gives a time complexity of O of n plus k log n, which is a bit better than the one of the previous solution because k can't exceed n. But this solution starts giving interesting time performance difference only when n is huge and k is small, because when k is close to n, O of n plus k log n is close to O of n log n, the time complexity of the previous solution. But when k is close to 0, O of n plus k log n is close to O of n. And for the space complexity, we have n for the priority queue, we get an O of n space complexity. We reached the end of this video. I hope that you understood the 3 solutions, and see you in the next one. Welcome back to the course. In this lecture, we will solve the symmetric tree problem. We have a binary tree, and we want to see if it's symmetric. In other words, if it's a mirror of itself. For example, this tree is symmetric, because if we take its left part, reverse it, we get its right part. And vice versa, if we take its right part, we reverse it, we get its left part. But this one is not symmetric. For example, if we reverse its left part, we don't get the right part. Okay, how to solve this problem? To check if a tree is symmetric, what we really need to check is that left and right subtrees are symmetric to each other. We will focus on that. You need to know that for tree problems, the solution is usually done recursively. We process the root, then we call the function on both subtrees, and we combine the results. For example, to get the sum of elements of a binary tree, we have the value of the root, then we recursively call the function on both subtrees to get the sum of their elements. After doing so, we return root value plus sum of left subtree plus sum of right subtree. This way of traversing is called depth first search, and it's how we solve the majority of tree problems. Let's go back to our problem. We have two trees root 1 and root 2, and we want to check if they're symmetric to each other. First case, both trees are empty. In that case, we return true because they're still symmetric to each other. There is nothing that breaks the condition. Second case, one tree exists but the other one doesn't. In that case, we directly deduce that they're not symmetric, because the node of the tree that exists doesn't even exist in the other one. It's empty. We return false. Third case, both trees exist but their roots don't have the same value. Here also, they're not symmetric, because in symmetric trees, the roots must have the same value, because when we reverse a tree, the root position doesn't change. And last case, both trees exist and they have the same root value. In this case, we still can't say that they're symmetric, because, okay, the roots have the same value, but we still need to check their subtrees. Having the same root value is not enough to say that they're symmetric. And if we take two symmetric trees, we can notice that they have the same root value, that the left subtree of the first one is symmetric to the right subtree of the second one, and that the right subtree of the first one is symmetric to the left subtree of the second one. We verified that root values are equal, so we need to check the remaining two conditions. And how are we going to do so? We're going to do so recursively. Because if you think about it, we're building a function that checks if two binary trees are symmetric, which is exactly what we need. This is why we will use the same function. It may sound hard to understand, but this is what recursion is about, a function calling itself. If you're not familiar with recursion, you should really have a look at it before continuing this course, because we will use it again in a further problem. If you want to learn recursion, you can check the course I made on the subject. It's a complete and well appreciated course that will let you be comfortable with recursion. Let's go back to our problem. We said that we use the function we're making. We call it on root1.left and root2.right, we call it on root1.right and root2.left, and we check that both calls return true. It means that both conditions are verified, that the left subtree of root 1 is symmetric to the right subtree of root 2, and that the right subtree of root 1 is symmetric to the left subtree of root 2. Let's quickly see an example. We want to check if this tree is symmetric, so we check if its subtrees are symmetric to each other. They have the same root value, so we check left subtree of root 1 with right subtree of root 2. Same root value, we check left subtree of root 1 with right subtree of root 2. Same root value, we check left and right. Same root value, and their children are both null, they will return true. Same root value in symmetric children, all conditions are respected, it returns true. Now right subtree of root 1 with left subtree of root 2, they have the same root value. Their children are both null, both calls return true. All conditions are respected, the call returns true. Back to here, all conditions are respected, the call returns true. Now right subtree of root 1 with left subtree of root 2. They don't have the same root value, the call returns false. Not all conditions are respected, the call returns false. We don't even need to check the second call because we already have a non-respected condition, the call returns false. The initial call returned false, so our tree is not symmetric. In code, let's first make our R-symmetric function. It takes two trees as parameter, root 1 and root 2. First case, both don't exist, we directly return true. Second case, one of them exists but the other one doesn't. And third case, they have a different root value. In both of these cases, the trees are not symmetric, so we return false. We write, if root 1 is none is not equal to root 2 is none, or root 1.val is not equal to root 2.val, we return false. And now in the last case, both trees exist and have the same root value, we still need to check subtrees. We check that root 1.left is symmetric to root 2.right and that root 1.right is symmetric to root 2.left. We do so by recursively calling the function twice, once with root 1.left and root 2.right, and once with root 1.right and root 2.left. Both of them need to return true, so we return the results combined with the AND operator. And now when our main solution function is symmetric, we first check that the input tree exists, because if it doesn't, we can directly return true. An empty tree is symmetric. Else, we check that its subtrees are symmetric to each other with the function we made now. We return r-symmetric root.left and root.right. That's it. For the time complexity, we're just performing a depth-first search traversal of the input tree, and DFS cos O of n time, where n is the number of nodes. And for the space complexity, a symmetric tree has to be balanced, and the call stack size needed by a recursive function that traverses a balanced binary tree is an O of log n. We got an O of log n space complexity. That's it for this lecture. We've seen an interesting problem on trees. I hope that you've been able to understand the solution. See you in the next lecture. Welcome back to the course. In this lecture, we will solve the generate parenthesis problem, a problem that we will solve using backtracking. By the way, in this course, I try to include problems on different patterns, binary search, hash table, backtracking, depth-first search, and so on. But one problem in each is not enough. This is why you need to study more problems. For that, I suggest you to have a look at my 50 popular coding interview problems course. It contains 50 problems different from the ones in this course, about many data structures and algorithmic techniques. You can have a look at the curriculum and reviews on the main page. Anyway, let's go back to our problem. We are given an integer n, and we are asked to generate all valid combinations of n pairs of parentheses. For example, with n equal to 3, here are all the valid combinations. First of all, what does a valid combination mean and how to check if a combination is valid? A combination that contains one type of parenthesis is valid if every opening parenthesis has its closing parenthesis, and it doesn't have a closing parenthesis without having an unused opening parenthesis before it. Let's see some examples. This combination is invalid because these opening parentheses don't have closing parentheses. The syntax is invalid. Second example, this combination is invalid because we have a closing parenthesis without an unused opening parenthesis before it. Last example, this one is valid because each opening parenthesis has its closing one, and there is no closing parenthesis without an unused opening one before it. Now, how to check if a combination is valid? To do so, we can maintain a stack where we push when we find an opening parenthesis and we pop when we find a closing one. The condition is that we don't try to pop from the stack when it's empty, and the stack has to be empty after we finish traversing the combination. Trying to pop from the stack when it's empty means that we have a closing parenthesis without an available opening one before it. All ones that we found before have been popped by all their closing parentheses. And the second condition is that the stack must be empty at the end, because still having elements in the stack after traversing means that we have opening parentheses that didn't get their closing one yet. In both cases, the combination is not valid. And because we have only one type of parentheses, round ones, we don't even need the stack. We can just use a variable div that represents the difference between the number of opening parentheses and the number of closing ones. It has to be 0 at the end, and if it becomes negative during the process, then it's not valid. Okay, but what's the relation with backtracking? In this problem, we're not asked to check if a combination is valid. We're asked to generate all valid combinations of n pairs. And we use backtracking because at each step of building the combination, we have two possibilities, adding an opening parenthesis and adding a closing one. And because we want all combinations, we try them both, because we get new ones when we add an opening one and other ones when we add a closing one. Also, in backtracking, we can have a condition where we backtrack without continuing. It's when we know that the actual branch won't lead us to a valid solution. In our case, it's when diff becomes negative. It means that the combination we built until now isn't valid. It's useless to continue building it. We know that it won't give us a valid combination anyway. Let's see an example. With n equal to 3, we get this recursion tree. If you're wondering why n starts at 6, it's because the n given as input represents the number of pairs, and in n pairs we have 2 n parentheses, so we multiply by 2 because we're adding 1 parenthesis by level. When we go to the left, we add an opening one and increment diff, and when we go to the right, we add a closing one and decrement diff. We can notice that we have branches that have been stopped earlier. Those are branches where diff becomes negative. As soon as diff becomes negative, we stop. Also, even with branches that created the combination of n pairs, we don't take all of them. We take only those where diff is equal to 0. Remember the validity condition. So at the end, here are the combinations that get added to our combinations array. In code, we start by creating a recursive function rec that will fill the combinations array. It takes as parameters n, the number of remaining parentheses to add, diff, the difference between opening and closing brackets, comb, the actual combination that we're building, and comps, the array of combinations, the one that we're searching for in our problem. The first base case is when diff becomes negative. Here we directly backtrack, we directly return to go back to the previous call. The second base case is when we've been able to add all the parentheses, we've been able to build a combination. But in this case, we don't automatically add it to our comps array. We first check if diff is equal to 0, remember the condition. So if diff is 0, we join the parentheses of our combination to form a string, and we add it to our valid combinations array. Else, we have the recursive case. We said that we have two possibilities, adding an opening parenthesis and adding a closing one. Therefore, we will have two recursive calls. For the first one, we add an opening parenthesis to our combination. Then when we call, n becomes n-1 because we have one less parenthesis to add. And diff becomes diff plus 1 because remember that we add 1 when we add an opening parenthesis. After the call, we remove the opening one we added to put a closing one. After doing so, we call the function again, but this time, diff becomes diff minus 1. Remember that we subtract 1 when we add a closing parenthesis. And after the call, we remove the parenthesis we added to backtrack to the previous call. And we made our function. By the way, we can even optimize a little bit by directly returning if diff is greater than n, because if it's the case, it means that we don't have enough remaining parentheses to close all our opening parentheses. Diff is greater than n, so we just return. If you're confused about what's happening here, have a look again at the recursion tree. And most importantly, you should learn more about recursion and backtracking. The method we're using here to generate all possible combinations. It's common to a lot of problems, you should really be comfortable with it. And now in the main solution function, we first create an array comps where we will put our valid combinations, and we call our recursive function to fill it. But the tricky part here is that we pass 2 times n as an argument, not n, because the n given as input represents the number of pairs, not the number of parentheses. And a pair is made of 2 parentheses, so we pass 2 times n. Our combinations will be of length 2 times n. After filling comps, we just return it. For the time complexity, in the worst case, when n is 0, we have a cost of n to join the parentheses. We write t of 0 is equal to n. And in the recursive case, n again removing from the combination costs O of 1, but we have 2 calls where the input size gets reduced by 1, n is becoming n-1. In total, t of n is equal to 2 times t of n-1 plus 1. Now we keep replacing. T of n is equal to 2 times t of n-1 plus 1, so t of n-1 is equal to 2 times t of n-2 plus 1. We replace. We simplify, and we get 4 times t of n-2 plus 3. We replace again. T of n-2 is 2 times t of n-3 plus 1. We replace. We simplify, and we get 8 times t of n-3 plus 7. This recurrence relation is a common one. We can already notice the general form. its t of n is equal to 2 power k times t of n minus k plus 2 power k minus 1. We have the value of t of 0, so we need to find the value of k to go to t of 0. N minus k equal to 0, so k is equal to n. We replace k by n, we get t of n is equal to 2 power n times t of 0 plus 2 power n minus 1. We know that t of 0 is n, we replace. We get t of n is equal to 2 power n times n plus 2 power n minus 1, which gives an O of n times 2 power n time complexity. Note that here n represents the length of the combination, which is 2 times the number of pairs given as input. Also, n times 2 power n is not the exact bound. The number of operations will be less than that due to branches where we backtracked earlier. O of n times 2 power n would be the exact bound if we had no condition on our combinations. If you don't know the technique I used to find the time complexity of this recursive function, it's called the substitution method. It's an important technique to know, you should learn about it. And for the space complexity, we have n plus 1 for the cul-de-sac size, the length of the longest branch in the recursion tree. But we also need to count the required space to store the combinations. The length of a combination is n, and it has 2 possible characters, so we have 2 power n possible combinations. And the length of each one of them is n, so we need n times 2 power n space to store them. We get O of n times 2 power n as space complexity. But not all of them are valid, we will need way less than n times 2 power n. N times 2 power n is just an upper bound. In reality, the required space for combinations is n times the number of elements after filling the comps array. We reached the end of this lecture. I hope that you understood this backtracking solution, and see you in the next one. Welcome back to the course. In this lecture, we will solve the gas station problem. We are given a circular list of gas stations where we can go from a station I to the station I plus 1, and the last one goes back to the first one. And we are asked to find the index of the station from where we start to be able to traverse all the stations and go back to the initial one without running out of gas. Note that we can only move forward. The gas tank starts empty. Gas of I represents the amount of gas at the station I. Cost of I represents the cost to go from the station I to the next one. The answer is guaranteed to be unique, and if the station we're switching for doesn't exist, return -1. We deduce that there will be at most one station from where we can traverse and be able to go back. For example, if we have these 10 stations, the output is 8, because when we start from station 8, we can go back to it without running out of gas. We start with no gas as mentioned in the problem. We add 4 gas of station 8 and we pay 1 to move to the next station. We add 5 gas of station 9 and we pay 2 to move to the next station. We add 1 and pay 5. We add 5 and pay 2. We add 3 and pay 2. We add 3 and pay 8. We add 5 and pay 2. We add 3 and pay 4. We add 1 and pay 2. We add 3 and pay 5. And we've been able to go back to station 8. You could see that the amount of gas never became negative, which is not the case for all the stations. For example, with station 1, we add 5 and pay 2, we add 3 and pay 2, we add 3, and here if we pay the 8 to move to the next station, the amount of gas becomes negative, which means that we can't continue. The station we started from is not the right one. Let's solve this problem. A brute force solution that directly comes in our mind is to simply simulate what happens with every station. And if we find one that respects the condition, we return its index. Let's try it with our example. With the first one, we add 1, we pay 5, and the cost becomes negative, directly eliminated. Next one, we add 5 and pay 2, we add 3 and pay 2, we add 3 and pay 8, and the amount of remaining gas became negative, not this one. Next one, we add 3 and pay 2, we add 3 and pay 8, and remaining became negative. Next one, we add 3 and pay 8, remaining became negative. Next one, we add 5 and pay 2, we add 3 and pay 4, we add 1 and pay 2, we add 3 and pay 5, and remaining became negative, not this one. Next one, we add 3 and pay 4, negative. Next one, we add 1 and pay 2, negative. Next one, we add 3 and pay 5, negative. Next one, we have plus 4 minus 1, plus 5 minus 2, plus 1 minus 5, plus 5 minus 2, plus 3 minus 2, plus 3 minus 8, plus 5 minus 2, plus 3 minus 4, plus 1 minus 2, plus 3 minus 5, and we've been able to go back to the station from where we started. We directly return it because we know that the answer is unique. In code, we create a function that takes as parameters the array gas, the array cost, and the index of the station from where we start. The goal of this function is to tell us if we can finish the cycle by starting from the station start. We first need a variable remaining that stores the remaining amount of gas. We also need a variable to store our actual position. Our initial position is the station from where we start, so we initialize I at start. And we also need a boolean variable started to know if we started walking yet or not. We need this variable in our loop condition. We need to keep looping until we go back to start. We write while I isn't equal to start or not started. Here, not started is important, because if we don't use it, we won't even enter the loop. Remember that I is initialized at start, so I and start are equal. We want them to be equal, but after traversing the cycle, not now. This is why we need the variable started, to know if we're in the case where I is equal to start because we didn't start yet, or because we traversed the cycle and I went back to start. Let's continue. Inside the loop, we set started to true, because we started. Then, we update remaining. We set that at the station I, we add the amount of gas in it, and we pay the cost to move to the next one. So we add gas of I and subtract cost of I. After doing that, if remaining becomes negative, it means that we couldn't go back to start. We don't have enough gas, we return false. Else, we move to the next station. The next station is usually at I plus 1, but we need to add modulus the number of stations to handle the case where we're at the last station. I becomes I plus 1 and modulus and it goes back to 0. We write I becomes I plus 1 modulus the number of stations. And if we finish the loop, it means that we've been able to go back to start, we return true. Now in our main solution function, we just try the function we made on each station as we did in the example, and we return the actual station as soon as the function returns true. And if the function fails with all stations, we return -1. For the time complexity, because the answer is unique, a possible worst case is this one. Because by starting from station 0, we traverse n stations before getting a negative amount. From station 1, we traverse n-1. From station 2, we traverse n-2, and so on. We get the sum n plus n-1 plus n-2 and so on until 1. After simplifying, we found that it's an O of n squared. We get an O of n squared time complexity. And a constant space complexity because we're not using input size related variables. O of n squared is slow for this problem. We're getting O of n squared because for each station, we're traversing again almost all the stations. Let's see how to optimize it. The main thing that you need to understand for the second solution is that if we start from a station at the index start and reach a negative amount at the station I, then all stations between start and I inclusive are not valid. We don't need to try them. We directly jump to I plus 1. Let me tell you why. We have the case where gas of start is smaller than cost of start. Here the loop stops directly because remaining becomes negative. It stops at start, so there are no other stations involved. Nothing to talk about here. But when gas of start is greater than or equal to cost of start, the loop moves to all the stations. It can traverse a bunch of stations before remaining becomes negative. For example, here when we start at station 4, remaining becomes negative at index 7. It means that stations 4, 5, 6, and 7 are all invalid. We start again from I plus 1, 8. But why? Gas of start is greater than or equal to cost of start. In our case, the difference is 3. And this 3 is considered as an advantage over starting from next stations. It's like a bonus. By starting from station 4, we have 3 more gas than starting from the next one, station 5. And even with that bonus, we didn't have enough gas to do a full cycle. We stopped at station 7. Even with that bonus, we couldn't go over station 7. So how do you want to go over it without that bonus? It's like you have $500 and they aren't enough to buy a particular PC, then you say, these $500 weren't enough, I'll try with 400s, maybe they will be enough. It's illogical. And this is why when remaining becomes negative, we don't try again from the station that comes after the one where we started. We skip all the ones we traversed. We start again from I plus 1. With our example, we start from the beginning, remaining becomes negative, we start from I plus 1. We add 5 and we pay 2, remaining becomes 3. We add 3, we pay 2, remaining becomes 4. We add 3, we pay 8, remaining becomes minus 1, negative. What we're gonna do now is to directly start again from here, without trying again from stations 2, 3. We add 5, we pay 2, remaining becomes 3. We add 3, we pay 4, remaining becomes 2. We add 1, we pay 2, remaining becomes 1. We add 3, we pay 5, remaining becomes minus 1, negative. Once again, we directly start again from I plus 1. We add 4, we pay 1, remaining becomes 3. We add 5, we pay 2, remaining becomes 6. And we finish traversing the array. The candidate is station 8. But it doesn't mean that it can do a full cycle. It just means that we can reach the end of the array without reaching a negative amount of gas. We didn't check the path before it. This is why I said candidate. It's a potential valid station. We don't know yet. To say that a candidate station is valid, by starting from there, remaining must never become negative when traversing the path from candidate to the end, but also when traversing the path from the beginning of the array to candidate exclusive. The first part of the cycle is what we verified during the traversal, and for the second part of the cycle, we just calculate the sum of gas from 0 to candidate minus the sum of cost from 0 to candidate. The result represents the remaining gas after traversing that path. And if by adding it to remaining the result stays positive, then candidate is a valid station, else we have no valid station. For example, here the sum of gas from 0 to candidate exclusive is 24, and the sum of cost from 0 to candidate exclusive is 30. The difference is minus 6. What remained from candidate to the end is 6. What remains in the path before candidate is minus 6. By adding them together, we get 0, which is positive. So candidate is the valid station. Question: what if we got a negative result here? Then we directly return minus 1, because there is no valid stations. But what if the valid station comes after the candidate? It's impossible. Once again, the station from where we started, candidate, has an advantage over next stations. We know that gas of candidate is greater than or equal to cost of candidate. So even if with that bonus we get a negative remaining amount of gas, it will also be the case for next stations. Let's jump to the code to understand all of this. Remaining starts at 0, and same thing for candidate, because at the beginning we assume that the first station is the candidate, the potential valid station. Now we start traversing stations. For each station, we update remaining gas, we add gas of I and subtract cost of I. And if remaining becomes negative, we say that we start again from I plus 1, it becomes a new candidate, and remaining becomes 0 because we will start again. After the loop, we calculate remaining gas of the path before candidate, the sum of gas minus the sum of costs of the path from 0 to candidate exclusive. Now we have three possible cases. We have the case where candidate is equal to n. It means that we reach the end of the array without finding a potential station. No station made it to the end of the array. We return minus 1. Second case, we have a candidate, but when adding prev remaining, we found a negative result. It means that it stopped somewhere in the path from 0 to candidate. We return minus 1. And third case, we have a candidate and remaining plus prev remaining is not negative. So candidate is the valid station from where we start to be able to do a full cycle. We return it. In code, if candidate is equal to length of gas, the number of stations, or remaining plus prev remaining is smaller than 0, we return minus 1. Else, we return candidate. We can even keep track of prev remaining in the first loop to avoid traversing again to calculate the sums. For the time complexity, we just have a loop that does n iterations. All other operations are in O of 1. We get an O of n time complexity where n is the number of stations, much better than O of n squared. And a constant space complexity because we're not using input size related variables. Basically in this solution, we search for the candidate, the station that made it to the end of the array without reaching a negative amount of gas. Then we check if it still bears up when traversing remaining stations, those in the path from the beginning of the array until going back to it. We reached the end of this video. I hope that you understood the optimized solution, and see you in the next one. Welcome back to the course. In this lecture, we will solve the course schedule problem. We have n courses labeled from 0 to n-1 inclusive that we need to take, but some of them are prerequisites to other. We cannot take a course before taking the other one. And we have to determine if it's possible to finish all the courses. So we are given an integer n representing the number of courses, and an array prerequisites where prerequisites of I is equal to AB means that you first need to take the course B before taking the course A. For example, if we have this input, the output should be false, because to take course 3 we must have taken course 0, and to take course 0 we must have taken course 1, and to take course 1 we must have taken course 3. Which is impossible. It's like we have a dependency cycle. This is why we cannot finish all the courses. We return false. But with this input, the output is true. We can take course 0, then course 3, then course 1, then course 5, then course 2, then course 4. Each course will have its prerequisite satisfied when taking it. How to solve this problem? Here we have elements, courses, and relationships between them, a course being a prerequisite of another course. And every time you face this situation, having elements and relationships between them, you should think of using a graph. I'm not saying that it will always give the best solution, but even if it doesn't, it will at least give you a way to visualize the problem, with vertices and links between them. In our case, the vertices represent courses, and edges represent dependencies. An edge from U to V means that we first need to take the course U before being able to take the course V. Okay, now we built our graph. We got a directed graph. What we will do with it? Our goal now is to search for a dependency cycle. If we find one, it means that it's impossible to finish all the courses. We return false. Else if we don't find one at all, it means that it's possible to finish them all. We return true. Basically, we're searching for a cycle in a directed graph. In a linked list, a classic way to check if there is a cycle is to traverse a linked list while saving visited nodes, and if we step on a node that we visited before, it means that there is a cycle. We can think of applying the same logic for a graph. We traverse with depth first search, for example, while using a set of visited nodes, and if we step on a node that has already been visited, it means that we have a cycle. We return false. By the way, if you don't know about depth first search, it's a way of traversing trees and graphs by diving deep into a direction until we can't move forward anymore, go back, try another way, and so on. I made a YouTube video about the subject that you can watch. You need to know about DFS before continuing this video. It's a prerequisite, intended pun. But this strategy doesn't always work. Here is a counterexample. We have this graph. Let's start traversing. We start, for example, from 2, we put it in visited. We move to 0, we put it in visited. We move to 3, we put it in visited. This one has no outgoing edges, we backtrack. This one has no remaining neighbors to traverse, we backtrack. From here we move to the second neighbor, 1, we put it in visited. We move to 4, we put it in visited. Then from here we move to 3, and it's already in visited, so our strategy would return false. Which is wrong, because we can totally finish all the courses here. We can start with 2, then 0, then 3, then 1, then 4. All prerequisites are respected. What's the solution then? Well, let me first talk about topological sort. We have a directed graph where vertices represent tasks and an edge from U to V means that U is a prerequisite of V. Topological sort is the process of finding a linear ordering of vertices such that each vertex comes after its prerequisites. In other words, for each edge from U to V, V must come after U in the ordering. For example, for this graph, here is a valid ordering. Note that a valid ordering is not always unique. It's possible to find other orderings that satisfy the condition. But topological sort is not always possible. It's not possible when the graph contains a cycle, like this one. B is a prerequisite of C, C is a prerequisite of D, D is a prerequisite of E, and E is a prerequisite of B, so we have no way to order them. Fortunately, while performing the topological sort, we can detect the existence of a cycle. If it happens, we just stop and say that we cannot have a valid ordering of vertices. And it's exactly what we want to do in our problem. We have courses, some of them are prerequisites to other ones, and we want to know if we can take all the courses. In other terms, if a valid ordering exists. Therefore, we will use topological sort, and if during the process we found a cycle, we return false. Otherwise, we return true because it means that we've been able to make an ordering. Okay, but how does topological sort work? A possible way to implement topological sort is depth-first search. Let's for example start from this vertex. We put it on the path stack. The path stack contains the vertices of the actual path. B is its neighbor, we go to it, and we put it on the path stack. E is its neighbor, we go to it, and we put it on the path stack. H is its neighbor, we go to it, and we put it on the path stack. Now H has no neighbors, it means that we can safely put it in our ordering, because there are no vertices that have to come after it. It's a prerequisite of no one. We put it in the order stack, and we backtrack to the previous node. Next neighbor is I, we go to it, and we put it on the path stack. Same again, it has no neighbors, we remove it from path stack and put it on order stack, and we backtrack. Next neighbor is F, we go to it. J is a neighbor, we go to it. It has no neighbors, we remove it from path stack. We put it on order stack, and we backtrack. Next neighbor is I, but it's already visited. It has no more unvisited neighbors, so all vertices that have to come after it in the ordering are visited. We can safely put this one, and we backtrack. This one also has no more unvisited neighbors, we can put it in order stack, and we backtrack. And the process continues like that until we traverse the whole graph. At the end, we get this ordering. We reverse it to get the order from the beginning to the end, not the opposite. In code, our DFS function takes as parameters the graph, the vertex from where we start, the path stack, the order stack, and the set of visited nodes. We start by adding our vertex to the path stack, just when we start traversing it. Then for each unvisited neighbor, we first add it to visited, and we call DFS with it as an argument to traverse it. After doing so for all the neighbors, we can safely put the actual vertex on the order stack. We pop it from path stack and give it to order stack. And in our main top sort function, it takes as an argument the adjacency list of our graph. It creates the visited set, the path stack, the order stack, then it visits each unvisited vertex with DFS. After doing so, the order stack is filled, we return it reverse to get the ordering from the first vertex to the last one, not the opposite. And starting from this algorithm, we can add instructions to detect a cycle. We find the cycle when we find a back edge, an edge that goes from a vertex U to a vertex V, where V is already in the path stack. Like here, we have A, B, C, D, E, then E has B as a neighbor, which is already on the path stack. This graph contains a cycle. B and E depends on each other. In code, our DFS function will now be a Boolean function. It returns if yes or no we've been able to make an ordering. What we add is that, before moving to a neighbor, we check if it's not already in the stack. If it's the case, we directly return false. We can't make a valid ordering. Also, if traversing a neighbor returns false, it means that we found a cycle when going from there. This is why, if the recursive call returns false, we also return false here. And if we've been able to traverse neighbors without getting a negative result, we return true. We could make an ordering. Know that to optimize checking for the existence of the actual vertex in the stack, it's better to use a set instead of a list. Searching in a set is an O of 1 time an average. Path stack now is of type set. At the beginning we add our vertex to it, after the loop we remove it, and we add it to order stack. And in our main solution function, we first need to build the graph, because as input we have the number of courses and the list of prerequisites, not the adjacency list. To build the adjacency list, we know the number of vertices, so we create an array of n empty arrays. Each one will contain neighbors of the course I. Now we traverse prerequisites. The problem says that prerequisite of 1 has to come before prerequisite of 0, so we create an edge from prerequisite of 1 to prerequisite of 0. In other words, we add prerequisite of 0 to neighbors of prerequisite of 1. Now that we've built the adjacency list, we can start traversing. But before, we create the visited set, the path stack which is also a set, and the ordered stack. Then for each unvisited course, we add it to visited. And if calling DFS with it returns false, it means that we couldn't build the order, we found a cycle, so return false, we can't study all the courses. And if the loop doesn't return false, it means that we could find an ordering, we can study all the courses, we return true. And we've been able to solve our problem. For the time complexity, we're just performing depth first search on a graph, and the time complexity of DFS is of length of v plus length of e, while length of v is the number of vertices and length of e the number of edges. Here the number of vertices is the number of courses, n, and the number of edges is m, the length of prerequisites list. We got an O of n plus m time complexity. And for the space complexity, we have the space for the adjacency list, length of v plus length of e, the space for the visited set, length of v, the space for the path stack and the order stack, length of v, and the space for the call stack, length of v. In total, we get 4 times length of v plus length of e, which is an O of length of v plus length of e, which is O of n plus m. Know that you may find a similar solution but with colors. Each vertex can have the color white, gray, or black. Compared to our solution, white means unvisited, gray means visited and in the path stack, and black means visited and not in the path stack anymore. We've put it in the order. And if we find a neighbor that is gray, it means that it's in the actual path and we found it again, so we have a cycle, we return false. Now we implemented topological sort with depth first search, but we can also implement it with breadth first search. Let me show you how. If you don't know about breadth first search, I made a YouTube video about it. I recommend you to watch it before continuing this one. The general idea of our second solution is to split our directed graph into levels. In the first level, we have vertices that have no prerequisites. We can directly start studying them. Once we finish, we can remove them from the graph. By removing them from the graph, some vertices won't have prerequisites anymore, because their prerequisites were courses we just studied, and they're satisfied. And these vertices represent the second level. We put them in our ordering and we remove them. After removing them, some vertices won't have prerequisites anymore. They represent the third level. We put them in our ordering and we remove them. And the process continues like that until we have no more vertices. But removing vertices from a graph costs some time because we need to update the adjacency list. Instead, we'll keep track of the in degree of each vertex, and when we traverse a vertex, we decrement the in degree of all its neighbors. The in degree of a vertex is the number of edges that are entering it. For example, the in degree of this vertex is 2. So when we remove a vertex that is going to it, we decrement the in degree. And if the in degree of a vertex becomes 0, it means that all its prerequisites are satisfied, we can traverse it, we put it in the queue. With this graph, we count the in degree of each vertex, we search for vertices with an in degree of 0, we put them in the queue, and we apply a classic BFS traversal. The difference is that when we pop a node from the queue, we start by putting it in the ordering array because it has no remaining prerequisites. Also, when we traverse a neighbor, we decrement its in degree, and if it becomes 0, we put it in the queue. Last thing, we don't need a visited set, because we're not putting a vertex in the queue until we finish traversing all vertices that are going to it, so we don't have the risk of traversing a vertex again. With this graph, this is what happens. In code, we create an array of n empty arrays as we did with DFS, but we also add an array of n zeros to store the in degree of each vertex. Now when filling the adjacency list, we also increment in degree of prerequisite of 0, because prerequisite of 0 is the vertex where the edge enters, so we increment its in degree. Now we create an array where we will put our ordering, and a queue. The queue initially contains vertices whose in degree is 0. After it, we start traversing. While the queue still contains elements, we pop a vertex, we add it to ordering because it has no unsatisfied prerequisites, and we traverse its neighbors. For each neighbor, we decrement it in degree, and if it becomes 0, we enqueue it, as explained earlier. After the loop, the order array is now filled. We return it. This time we don't need to reverse it because we started by putting vertices of level 0, then 1, and so on. With this topological sort algorithm, we can also detect cycles. When the graph contains cycles, what happens is that at some point of the process, we will have no more vertices with an in degree of 0, which means that nothing will be inserted in the queue, the process stops, and the order array will contain less than the total number of vertices. We will deduce that the process couldn't continue because there is a cycle. And in our problem, we just want to know if we can make an ordering or not. This is why after the loop, we will just compare the length of the order array with n, the number of courses. If they're equal, the algorithm returns true, else it returns false. So we keep the same code, we just change the return statement. We return length of order equal to n. For the time complexity, we're just applying breadth first search, which has an of length of v plus length of a time complexity, of n plus m in our problem. And for the space complexity, we have length of v plus length of a for the adjacency list, length of v for the in degree array, and length of v for the queue and the order array. 3 times length of v plus length of e gives of length of v plus length of e, which is of n plus m in our problem. We get an of n plus m space complexity. We reached the end of this video. In this one we solved the course schedule problem with 2 different ways. I hope that you understood them both, and see you in the next one. Welcome back to the course. In this lecture we will solve the kth permutation problem. With a range of numbers from 1 to n inclusive, we can make n factorial permutations. By labeling them in order starting from 1, you are asked to return the kth permutation. For example, with n equal to 3 and k equal to 3, here are the 3 factorial permutations of 1, 2, 3 labeled and in order. K is 3, so we return the third one, 2, 1, 3. The first solution that may come in your mind is obviously the brute force solution, generating all the permutations, then return the kth one. We give to the function the range from 1 to n inclusive, then we return the one at index k minus 1. Remember that an array is 0 indexed, so the kth one is at index k minus 1. But the problem with this solution is that with n elements, we can make n factorial permutations of length n, and it costs n times n factorial to generate them. We get an of n times n factorial time complexity solution, which is extremely slow. We deduce that the trick to solve this problem is to be able to find the kth permutation without generating the permutations, and this is what we will see now. Let's take n equal to 4. Now take a paper or notepad software, list all the permutations of 1, 2, 3, 4 in order, and tell me what do you notice. I want you to take some minutes to analyze the structure of those permutations. Here are all the permutations. We have a total of 4 factorial permutations, 24. We can notice that these 24 permutations can be divided into 4 parts. The first one contains permutations that start with 1, the second one contains permutations that start with 2, and so on. Let's suppose that we want to find the 16th permutation, k equal to 16. If we label them starting from 0, it means that we want to find the permutation 15, because 16 is when we label them starting from 1. The question now is, can we find what part among these 4 parts the permutation 15 will be? The answer is yes, by using math. We know that the first part contains permutations from 0 to 5 inclusive, the second one from 6 to 11 inclusive, the third one from 12 to 17 inclusive, and the last one from 18 to 23 inclusive. To find which one, we just divide k by the length of a part, which is 6 in our case. 15 divided by 6 gives 2, so the permutation 15 won't be in the part 0, won't be in the part 1, but it will be in the part 2. Know that we're working with 0 index labeling. We know that the part 2 contains permutations that start with 3, so we already know that our kth permutation will start with a 3, and it will be one of these permutations. Let's continue. What's gonna happen now is that the search space will be reduced. Now we know that our kth permutation will be in these 6 permutations. We need to update variables. K needs to be modified. Initially, we were searching for permutation 15 among all the permutations. But in this group of 6 permutations, we're searching for permutation 3. Why 3? Because 15 modulo 6, the length of the part, is 3. K is 15 when we start from permutation 0, but in this particular part, if we label permutation starting from 0, we're searching for permutation 3. N also represents the number of remaining elements of the permutation defined, and we found 1, so we decrement, and becomes 3. N factorial also changes, it becomes 3 factorial, 6. Same thing for path length, it also gets updated, 6 divided by 3 is 2. We also remove 3 from unused elements because we already found its place in the permutation, and our permutation doesn't contain duplicates. We can divide these 6 permutations into 3 parts of 2 elements. The first part contains permutations whose the second element is 1. The second part contains permutations whose the second element is 2. And the third part contains permutations whose the third element is 4. 1, 2, and 4 are the elements that we didn't use it in our permutation. Case 3 now, can we find the part kth permutation belongs to? Yes, once again, we divide by the part length. 3 divided by 2 gives 1, so the kth permutation will be in part 1. And we know that permutations of part 1 have 2 as second element, so the second element of our permutation will be 2. Again, the search space will be reduced. We know that our kth permutation will be in these 2 permutations. This is why we update the variables. K gets modified, as we did previously, it becomes K modulus the length of a part. 3 modulus 2 gives 1. It means that among these 2 permutations, we're searching for permutation 1. N gets decremented, it becomes 2, which changes the value of n factorial. 2 factorial is 2, which also changes the value part length. N factorial divided by n is 2 divided by 2, which is 1. We can divide these 2 permutations into 2 parts of 1 permutation. The first part contains permutations whose the third element is 1. And the second part contains permutations whose the third element is 4. To know the path the kth permutation belongs to, we divide by the path length. The path length here is 1, and 1 divided by 1 gives 1. Our permutation will be in part 1. Permutations of part 1 have 4 as a third element, so the third element of our permutation will be 4. We reduce the search space. We know that our permutation will be in this part of 1 permutation. We update variables, k becomes k modulus the part length, 1 modulus 1 is 0, n becomes 1, n factorial becomes 1, part length becomes 1, and we remove 4 from unused elements. We divide this 1 permutation into 1 part of 1 permutation. The first part will contain permutations whose 1 is the 4th element. The length of a part is 1, and k divided by 1 gives 0, so our kth permutation will be in part 0. And permutations of part 0 have 1 as 4th element, so the 4th element of our permutation will be 1. Now n becomes 0 and it gets decremented, so we finish the process. The kth permutation is 3, 2, 4, 1. We found it without generating all the permutations. If you didn't understand what we've been doing here, let me show it to you in another way. You first need to understand how our permutations generated. At the beginning, we have n choices, for in this example. And because we want all the permutations, we try all possibilities. When we add 1, when we add 2, when we add 3, and when we add 4. This is why you're seeing 4 branches at the beginning. And we're talking about permutations without repetitions, so when we take an element, we remove it from possible choices. This is why when we take 2 at the beginning, for example, that branch creates 3 branches only, not 4. 1 when we add 1, 1 when we add 3, and 1 when we add 4. You can see that we didn't add 2 again. Then when we take 4 for example, we have 2 choices left, 1 and 3. We get 2 new branches only. Then when we take one of them, we have 1 choice left, the one we didn't take. But in our problem, we want to find the kth one. The way we solve this problem is by using math to calculate what branch we should go from to reach the combination we're searching for. Imagine that you have 1000 books labeled from 0 to 999. Let's say that you're searching for the book 436. You remember that these books are organized into 10 boxes of 100 elements. The first one contains books from 0 to 99, the second one from 100 to 199, and so on. How to know which box to search in? You simply divide the number of the book you're searching for by the size of a box, because here they have the same size. 436 divided by 100 is 4. We search in box 4. We still didn't find the book, but we reduced the search space. Now we will search for book 36 in this box of 100. Why? Because 436 modulus 100, the path length, gives 36. Once again, the 100 books of the box 4 are organized in 10 boxes of 10 books each. The first one contains books from 0 to 9 after 400s, the second one from 10 to 19 after 400s, and so on. The box size is 10, 36 divided by 10 gives 3. We search in box 3. In that box 3, we search for book 6 because 36 modulus 10 is 6. And so on until we find the book, without traversing all the books. And basically, this is what we did to solve this problem. Let's try to generalize. At the beginning, we have n, k, and unused that contains elements in the range from 1 to n inclusive. Now, while n is greater than 0, we start by calculating the part length. It's n factorial divided by n. After it, we calculate the index of the next element to put in the permutation. Remember that we calculated by dividing k by the path length. After we calculate it, we add unused of I to the permutation, and we delete it from unused. We add unused of I because it represents the common element in the ith path. Then, we decrement n, and k becomes k modulus path length, to get its new position in the path that we choose. We keep repeating that, and when a becomes 0, we have our kth permutation, and we solve the problem. In code, we have a function that takes as parameters n and k, the given input. We create an empty array for the permutation we're searching for, then we create unused. It contains elements of the range 1 to n inclusive. After it, to avoid always recalculating n factorial, we create an array fact where fact of I represents I factorial. It contains n plus 1 elements to have the values from 0 factorial to n factorial. To fill it, we know that 0 factorial is 1, then for remaining elements, we just take the value of the previous cell and we multiply it by I. For example, with 5, we get 1, 1, 2, 6, 24, 120. Now, we decrement k because k represents the position of the permutation with 1 index labeling, but we're working with 0 index labeling, so k becomes k minus 1 to fit. We're working with 0 index labeling to simplify the math. We get the right result when we divide and use modulus. We can start the loop now. While n is greater than 0, path length is n factorial, fact of n, divided by n. Then, the index of the next element to take is k divided by path length. After getting the index of the next element, which is I, we add unused of I to our permutation, and we delete the element at index I from unused. Before moving to the next permutation, we decrement n, and k becomes k modulus path length. After the loop, our permutation is built. We just join its elements into a string and return it. We return the kth permutation as required by the problem. Basically, the solution we made now uses math to keep calculating the path that the kth permutation belongs to, because by knowing it, we know what is the next element to take from unused, which is the array of elements we didn't use yet. For the time complexity, creating unused costs n, creating fact array costs n plus 1, and filling it costs n. Then the while loop gets repeated while n is greater than 0, and n gets decremented at each iteration, so the number of iterations is equal to the initial value of n. Inside it, all operations are in O of 1, except popping the element I from unused. We can have the case where we need to shift all the elements to the left, and n to join the elements of the permutation. We have 4n plus n squared plus 1, we get an O of n squared time complexity, way better than O of n times n factorial of the first solution. And for the space complexity, we have n for unused and permutation, and n plus 1 for fact array. 2n plus 1 gives us an O of n space complexity. We reached the end of this video. I hope that you at least understood the general idea of the second solution, which is dividing the permutations into parts with a common element and calculating which part the kth permutation belongs to. See you in the next lecture. Welcome back to the course. In this lecture, we will solve the minimum window substring problem. We have two strings s and t, and we are asked to find the shortest substring of s that contains all characters of t. If such a substring doesn't exist, return the empty string. For example, if we have this input, as output we get CEABEBA is the shortest substring of s that contains all characters of t. In other words, 2 a's, 1 b, and 1 c. First of all, how can we know that a string contains all characters of another one? We can know it by having the counter of frequencies of each string, the one we use in the valid anagram problem. If frec1 is the counter of s1 and frec2 the counter of s2, for every distinct character of s2, frec1 of ch must be greater than or equal to frec2 of ch. In other words, s1 must have at least the number of occurrences of ch in s2. In code, we write, for each ch in frec2, if frec1 of ch is smaller than frec2 of ch, we return false. After the loop, we return true. Knowing this, we can already think of a solution, the brute force solution, which covers all possible substrings of s while keeping track of the shortest one that has all characters of t. In code, we can add an early exit condition. If t is longer than s, we can't find a substring that satisfies the condition. There isn't enough characters. We directly return the empty string. Same result when t is empty. We can return the empty string, because technically the empty string contains all the characters of the empty string. Else, we first create a counter for t, to know the frequency of each character in it. Let's name it frec_t. We also need the string shortest that represents the shortest valid substring that we found until now. It initially has n plus 1 characters to be sure that it gets updated as soon as we found a valid substring. Now we start traversing substrings of s. To do so, we start by traversing the lengths, because we will start by traversing substrings of 1 character, then substrings of 2 characters, and so on. This is why length goes from 1 to n inclusive. Inside it, we traverse starting positions, because with the same length, we have the substring that starts at index 0, the one that starts at index 1, and so on. But I doesn't go until the end, to avoid going out of bounds when adding the length. I goes from 0 to n minus length inclusive. We have the starting position, which is I, we have the length of the actual substring, so we can extract it. The actual substring is the one between I inclusive and I plus length exclusive. Now that we got the substring, we create a counter for it. Let's name it frec_s. After it, we check if the actual substring replaces the shortest one we found until now. For that, two conditions. The actual substring must contain all characters of t. We can know it with the function we made. And it must be shorter than the actual shortest one. The length of the actual substring is length, so if length is smaller than length of shortest, we replace. Shortest becomes the substring. After the loop, we don't directly return shortest, because it's possible that we didn't find any substring that contains all characters of t. To know that, we check the length of shortest. If it's still n plus 1, it means that it didn't get updated. We return the empty string as required by the problem. Else, we return shortest. Basically, we return shortest when its length is at most n. For the time complexity, let's say that n and m are lengths of s and t respectively. We have n for building frec_t and n plus 1 for creating shortest. Then we have n iterations for the outer loop, n minus length plus 1 iterations for the inner loop, and inside it, the cost of extracting the substring and generating the counter depends on length. We also have the cost of checking if it contains all characters, which is m, because in the function which covers characters of frec_t, their number is at most m. We get this sum, which is equal to 1 divided by 6 times n plus 1 times 3n plus 2n plus 4. We simplify, and in the worst case t is shorter than s, so m is smaller than n, we get an O of n cubed time complexity. And for the space complexity, we have n for frac t, n plus 1 for shortest, n for sub, and n for frac s. We get 3n plus m plus 1, which gives an O of m plus m space complexity. This solution is obviously very slow, it's not the best one. This is why we will move to the second solution. Inside the inner loop, we have a cost of length to extract, a cost of length to generate the counter, and a cost of m to check if it contains all characters. What if we try to reduce this cost to O of 1, to get a constant cost per inner loop iteration? Follow me well. How can we extract the substring in O of 1? In reality, we won't need to extract the substring in our second solution. We will just work with the start and end indexes of the substring, which are I and I plus length. We already know them. Second thing, how can we generate the counter of the actual substring in O of 1? The trick is to not always build the counter again. We will use the one of the previous substring. Let me show you how. Imagine that we have this string S, ABCADECEBAC. And the first substring of 5 characters has this counter, 2 A's, 1 B, 1 C, and 1 D. Starting from this counter, how can we get the counter of the next substring of 5 characters, which is this one? To do so, we just decrement the number of occurrences of the character that went out of the window and increment the number of occurrences of the character that went in the window. The one that went out is A. It was in the first substring but not in the second. We decrement fracs of A. It becomes 1. And the one that went in is E. It's in the second substring but not in the first one. We increment fracs of E. It becomes 1. And we got the new counter in O of 1, because no matter the length of the substring, we need to work on 2 characters only, the one that went out and the one that went in. There will always be only 2 because we're moving by 1 position at a time. Then for the next substring, same logic. The one that went out is B, so we decrement fracs of B. And the one that went in is C, so we increment fracs of C. And the process continues like that for all substrings of length 5. The technique we're using here is called sliding window. In our example, we were using a window of length 5. Then to move to the next substring, we don't start again from the beginning. We just move the window by performing the necessary changes. And we just focus on what went out of the window and what entered, not what's inside, because it won't change. Last thing to optimize, the cost of checking if it contains all characters. The cost is actually m, because we need to traverse characters of frac t, but let me show you how to optimize it. In our example, t is ABCA. It has 3 distinct characters A, B, and C, so we have 3 conditions to respect to say that our substring contains all characters of t. The conditions are at least 2 occurrences of A, at least 1 occurrence of B, and at least 1 occurrence of C. The idea to avoid always traversing all the characters, which can cost m, is to keep track of how many conditions are satisfied. And if for the actual substring the number of satisfied conditions is equal to the length of frac t, which is the number of distinct characters of t, then the actual substring contains all characters of t. It's a valid one. Okay, but some characters are going out of the window and some of them are entering, which means that when moving the window, some satisfied conditions can become unsatisfied and vice versa. Some unsatisfied conditions can become satisfied. How to handle that? To do so, after incrementing the number of occurrences of the character that went in, if it's in frac t and frac s of went in becomes equal to frac t of went in, it means that we didn't have enough occurrences of the character that went in, and now we do. So when new condition is satisfied, we increment satisfied. And before decrementing the number of occurrences of the character that went out, if it's in frac t and frac s of went out is equal to frac t of went out, it means that we had enough occurrences of the character that went out, but after decrementing, we won't, because frac s of went out will be smaller than what's required. This is why we decrement satisfied. A condition that was satisfied before is not satisfied anymore. And we decrement fracs of went out obviously. For example, here we have these strings s and t, and we're at this window of 7 characters. The conditions are at least 2 occurrences of A, at least 1 occurrence of B, and at least 1 occurrence of C. Here we have 1 occurrence of A, 2 2 occurrences of B and 1 occurrence of C. Only 2 conditions are satisfied, not enough. Let's move the window. Now E went out, but we don't care because it's not a character of T. We decrement in fracs, but nothing happens. And A went in, we increment fracs of A, and it becomes equal to frac T of A. We satisfy the new condition. The number of conditions is equal to length of frac T, so this substring is valid. It contains all characters of frac T. All conditions are satisfied. We move the window. Now C went out of the window, and its number of occurrences in the substring is equal to the number of occurrences in T. So when we decrement, because it went out, the condition becomes unsatisfied. We don't have enough C's anymore. And D enters the window, but we don't care. It's not a character of T. Now the number of satisfied conditions is smaller than what's required. This substring doesn't contain all characters of T. And the process continues like that. Once again, no matter the length of the window, we're dealing with 2 characters only, the one that went in and the one that went out. So checking if the actual substring is valid costs O of 1. We've been able to optimize extracting the substring, generating the counter, and checking if the substring is valid. We've seen how to do all of these in O of 1. But we didn't see the code yet. Let's move to the code. We keep the same elixir condition. We generate the counter of T, but now we don't save the shortest string itself. We just save its start and end position. Initially, shortest starts as a string of n plus 1 characters, so we initialize start and end at 0 and n plus 1 respectively. Now we start traversing lengths. What we were doing in the example is to update fracs according to characters that went in and out compared to the previous position of the window. But to do so, we first need an initial window that starts at 0 and whose the length is length, and we traverse it normally to fill fracs and count the number of satisfied conditions. We create fracs and we create satisfied, a variable to keep track of the number of satisfied conditions. It initially starts at 0 because we didn't start traversing characters of S yet. We didn't satisfy any condition. Then we traverse characters of the first window. For each character CH, we increment fracs of CH, and if CH is a character of T and fracs of CH becomes equal to frac T of CH, then the number of occurrences of CH became enough. A new condition is satisfied, we increment satisfied. After processing the first window, we check if it's a valid substring before moving to other ones, and if it should replace the actual shortest one. If satisfied is equal to length of frac T, the number of conditions, and length is smaller than the length of the actual shortest substring, which is end minus start, we replace. Start and end become 0 and length respectively, the boundaries of the first window. Now we can start traversing other substrings of the same length. I starts at 1 and not 0 because the first substring, which is the first window, is already processed. We start from the second one. We want to work with the character that went out of the window and the one that went in, but where are them? The actual substring is between indexes I inclusive and I plus length exclusive. The character that went out comes just before the window, so its index is I minus 1. And the one that went in is the last character of the window, its index is I plus length minus 1. We can start working. The character that entered the window is at position I plus length minus 1, so we increment fracs of S of I plus length minus 1. Now if it's a character of T and its number of occurrences in the substring became equal to the number in T, it means that a new condition is satisfied. We write, if S of I plus length minus 1 in frac T and fracs of S of I plus length minus 1 is equal to frac T of S of I plus length minus 1, we increment satisfied. After it, we work with the character that went out, the one at index I minus 1. If it's a character of T and its number of occurrences in the substring is equal to its number of occurrences in T, it means that a condition was satisfied but not anymore, because we will decrement fracs of S of I minus 1. So it will become smaller than frac T of S of I minus 1, not enough occurrences of S of I minus 1 anymore. We write, if S of I minus 1 in frac T and fracs of S of I minus 1 equal to frac T of S of I minus 1, we decrement satisfied. We lost a satisfied condition. After it, with decrement frex of s of I-1. Now that we know the number of satisfied conditions by the actual substring, the one between I and I plus length, we can check if it replaces the actual shortest one. We write, if satisfied equal to length of reg t and length is smaller than end minus start, we replace start and end by I and I plus length respectively. We found a shorter string that contains all characters of t. After the loop, start and end represent the boundaries of the shortest substring, but only if we found one. If end minus start is greater than n, then we didn't update start and end, we return the empty string because we didn't find any valid substring. Else, we return the part of s between start inclusive and end exclusive. What about the time complexity? We have n for building frec t, n iterations for the outer loop, then inside it, we have length iterations for the first loop, n minus length iterations for the second one, and all operations inside them are in O of 1, plus n for returning the part of s. Length plus n minus length gives n, and we can ignore m, we get an O of n squared time complexity. The space complexity doesn't change. You can see that now we've been able to reduce the time complexity from O of n cubed to O of n squared. Isn't enough? No, we can do better. When using sliding window, we have the case where the window size is fixed. For example, if we have an array of integers and we are asked to find the k consecutive elements with the greatest sum, we use a window of size k. We will move it, but we won't change its size because we know that the subarray we're searching for is of length k. However, in our problem, we don't know the size of the shortest substring that contains all characters. This is why we tried all possible lengths, which covers substrings of length 1, then those of length 2, and so on, which resulted in an O of n squared time complexity. But we have another way of manipulating the window. Instead of sliding the window by one position, in other words, extend it from the right by 1 and reduce it from the left by 1, what we can do is to extend it from the right by 1, but reduce it from the left by a number of times that is between 0 and the length of the window, depending on what we want to do. Let's apply to our problem. The idea of the strategy that we're gonna use is to find the shortest substring that ends at the actual index of right that respects the condition, which is containing all characters of t. And obviously keeping track of the shortest one among them all, the one that will be returned at the end. Let's start. For the first index, we find an a, but no condition is satisfied, we need two a's. Next index, we find d, we don't care about it. Next index, we find c, a condition is satisfied. Next index, f, we don't care. Next index, e, we don't care. Next index, b, a second condition is satisfied, but not all of them. Next index, e, we don't care. Next index, c, we have two c's now, but a condition is still missing. Next index, e, we don't care. Next index, a, we now have two a's, which is enough to satisfy the last condition. All conditions are satisfied now, it means that the substring from left to right inclusive is valid. But is it the shortest one that ends at the index right? Not sure, because we may have characters that we don't care about. By characters that we don't care about, I mean characters that we can remove without breaking the validity of the actual substring. And these characters are characters that are not in t at all, and characters of t that are in excess in our substring. For example, if we need 2 c's only and we have 5 c's in our substring, we can remove the first 3 ones to make the substring shorter while still satisfying the condition. Remember that our goal is to get the shortest valid substring. We cannot remove from the middle because characters of a substring must be adjacent, and we cannot remove from the right because we're searching for the shortest valid substring that ends at the actual position of right. So we can only remove from the left. We keep removing while the character at position left is a character we don't care about. Here the character at left is a, it's in t, and it's not in excess. We need 2 a's and we have exactly 2, so this one is important, we cannot remove it. We finish removing from the left, so the shortest substring that ends at right is this one. Its length is smaller than the actual shortest one, we update. We move to the next position of right, we find a b. The one at left is still important, so the shortest one is this one, but we don't update because it's not the global shortest one. Next position, we find an E. The character at left is still important. Next position, we find a B. The character at left is still important. Next position, we find an A. And here is where things change, because the character at left is not important anymore. The reason behind it is that we found another A, which means that the character A is now in excess. We can remove the first one without breaking the validity. We remove A and we decrement its number of occurrences. Let's see if we can continue removing. D is not an important character, it's not in T, we remove it. C is in T, but we have more than enough. We have 2 C's while we need only 1. We remove and decrement its number of occurrences. F is not in T, we remove. E is not in T, we remove it. B is in excess, we remove it. E is not in T, we remove it. C is in T and it's not in excess, so we stop removing. We found out that the shortest valid substring that ends at right is CEABEBA, and its length is 7, smaller than the length of the actual shortest one. We replace. Let's continue. We move to the next position of right. By the way, if you're wondering why aren't we going back to the beginning when we increment right, it's because we know that characters before the actual position of left aren't important. We don't need them for the actual substring. We found the D, the character at left is still important, and we don't update because the length is not smaller than 7. Next position, we find F, the character at left is still important, and we don't update. Next position, we find the C, which means that the character at left is not important anymore. The character C is in excess, we can remove it. E is not in T, we also remove it. A is important because it's in T and it's not in excess, we stop removing. We get A, B, E, B, A, D, F, C, which is not shorter than the actual shortest, we don't update. We continue, we find D and A is still important. Next position, we find F, A is still important. Next position, we find C and A is still important. Basically it will continue like this for the next 5 positions, and there is no update because the substring is getting longer. We're not being able to remove from the left. And in the next position, we find an A, so the one at left is not important anymore. We remove it. B is in excess, we remove it. E is not in T, we remove it. B is still in excess, we remove it. A is not in excess, so we stop. The substring is ADFCDFCBFCBEA, but not short enough to update. Last index, we find D and A is still important. We don't update, and we finish traversing S. The global shortest substring that contains all characters of T is the one between indexes 7 and 13 inclusive. It's CEABEBA. Take some seconds to process what you've seen until now before continuing the video. Let's move to the code. We keep the same early exit condition. We build frect as we did previously. We initialize start and end at 0 and n respectively. We initialize satisfied at 0. We create frax which is empty at the beginning, and we add a variable left that represents the left boundary of the window. Here n starts at n and not n+1 because now n represents the last index of the window. It's inclusive. Also, you can see that we created frax and satisfied outside the loop because we won't traverse lengths as we did in the previous solution. We don't need to do that. We will directly traverse positions of right, the right boundary of the window. For each position right, we increment the number of occurrences of the character obviously, and we check if we satisfied a condition. As we did in the previous solution, if s of right is in frect t and frax of s of right is equal to frect t of s of right, we satisfied a condition, so we increment satisfied. Basically in the part before satisfying all the conditions, this is what we need to do only, incrementing the number of occurrences and checking if we satisfied a condition. Remember that we're expanding from the right only, left remains 0. But once we satisfy all the conditions, which we can verify with this condition, satisfied equal to length of frect t, we can start removing from the left. We don't know how many characters are we gonna remove from the window, so we use a while loop. We said that we keep removing characters while the character at left isn't important, and a character that is not important means that either it's not a character of t or it's in excess, means we have more than what's required. We write while s of left not in frac t or fracs of s of left greater than frac t of s of left. Inside the loop, we remove the character, which means that we decrement its number of occurrences in fracs and move left to the next position. Now that we removed all unnecessary characters, we got the shortest valid substring that ends at the actual position of right, is the one between left and right inclusive. What do we do now? We check if it replaces the actual global shortest one. The length of the substring we found now is right minus left plus 1 because this time the right boundary, which is right, is included in the window. And the length of the actual global shortest one is end minus start plus 1 for the same reason. So if right minus left plus 1 is smaller than end minus start plus 1, we update. Start and end become left and right respectively. After the loop, almost same return statement, we just add plus 1 because end is included in the window now. If we could update at least once, we return the part of s between start and end inclusive, else we return the empty string. By the way, you can see that this time we weren't checking if we lost a satisfied condition, because we stop removing as soon as we reach the minimum required occurrences, we never go below it. This is why when the character at left was important, we weren't removing at all, not like in the previous solution where we were removing no matter what. For the time complexity, we have m for building frac t and the outer loop does n iterations. It's true that we have an inner while loop, but the tricky part is that its number of iterations doesn't exceed n in total. I repeat, in total. Why? Simply because at each iteration of the while loop, we're removing a character, and we have n characters. Remaining operations are all in O of 1, so the cost of the outer loop is an O of n. Yes, O of n only, not more. We add plus n for extracting the output, and in total we have m plus O of n plus n, which gives an O of n plus m time complexity, better than O of n squared. And for the space complexity, same as the previous solution, O of n plus m. And we've been able to solve the problem in O of n plus m time only, by using a bunch of interesting optimizations. That was a tough problem. I hope that you understood how we built our optimized solution, and that you will be able to use it to solve all the problems. We've reached the end of this video. It was a long one, but I tried to detail each operation to let you understand what is each line of code doing and how the algorithm works in general. See you in the next video. Welcome back to the course. In this lecture, we will solve the largest rectangle in histogram problem. We are given an array height that contains the height of each bar in the histogram, and we are asked to return the area of the largest rectangle in the histogram. Note that each bar has a width of 1. For example, if we have this input, here is the largest rectangle. Its area is 7 times 5, which gives 35. How can we solve this problem? Let's for example take this bar. It has a height of 2. Now, can you tell me what's the largest rectangle of height 2 that passes from this bar? It's this one. But how did we know? Let's start from that bar and keep expanding. Can we expand to the left? Yes, 3 is greater. Can we expand? No, because we have no more bars from the left. From the right now. Can we expand? Yes, 4 is greater. Can we expand? Yes, 5 is greater than 2. In other words, this bar is higher, so our rectangle can pass from it. Can we expand? Yes, 7 is greater. Can we expand? Yes, 6 is greater. Can we expand? No, we can't expand from here because 1 is smaller than 2. So if we expand, the rectangle won't be fully included in the histogram. It's not a valid rectangle. We expanded as much as possible from both sides. We got that the largest rectangle that passes the initial bar is this one. It has an area of 12, 2 times 6, the height multiplied by the width. And we can apply this strategy on each bar while keeping track of the greatest area. At the end, we will have found the greatest area, because the largest rectangle necessarily passes from a bar that has the same height as itself. The reason behind it is that, if the rectangle is shorter than all the bars it passes from, it means that it's not the largest one. We can still make it bigger by increasing its height. And if it's taller than at least one bar, then it's not fully included in the histogram. It's not a valid rectangle. With this example, with the first bar we get this rectangle, with the second bar we get this rectangle, and so on. At the end, the greatest area that we find is 35, the area of this rectangle. In code, we initialize max area to 0 because we didn't traverse any rectangle yet. Then for each bar I, we expand from both sides. From each side, we keep expanding while the bar is still higher or as high as our bar, so we stop when we find a shorter one or when we have no more bars. Left starts at the actual position. Then while the previous bar exists and is at least as high as the actual bar, we expand. We move left by one position to the left. Same logic with the right side but by incrementing. Right starts at I, then while the next bar exists and is at least as high as the actual bar, we expand. We move right by one position to the right. While right plus 1 smaller than n and heights of right plus 1 greater than or equal to heights of I, we increment right to take it to the right. Now that we know boundaries of our rectangle, we need to calculate its area. The area of a rectangle is the height multiplied by the width. The height here is the height of the initial bar, height of I, and for the width is the distance between left and right plus 1, right minus left plus 1 because both left and right are included in the rectangle. Now we check if we replace. Max area becomes the max between its actual value and the area of the actual rectangle, heights of I multiplied by right minus left plus 1. After the loop, we just return max area. For the time complexity, we're traversing the n bars, and for each bar, when searching for left and right boundaries, we may traverse the whole histogram. This is why we get an O of n squared time complexity in the worst case. The worst case happens when all bars have the same height. And for the space complexity, it's constant, we're just using int variables. This solution is slow, let's move to the next one. There are interesting properties to know about the shortest bar. The first one is that, by starting to make a rectangle from it, we can expand it until the boundaries of the histogram, because there are no shorter bar to stop the expansion. Second one, the rectangle starting from any other bar can't pass through it, except if it has the same height, but we get the same rectangle in that case. So, the shortest part is like a wall. Any other rectangle will either be on its left side or on its right side. From these two information, we can make a solution based on divide and conquer. We search for the shortest bar, and we have a rectangle that traverses the whole histogram. We also recursively search for the largest rectangle in the left side, the largest rectangle in the right side, and we take the maximum among these three rectangles. It represents the largest rectangle in the whole histogram. The reason behind it is that, because our bar is the shortest one, we can't have a taller rectangle that joins the left and the right side. A taller rectangle will either be in the left part or in the right part, so we don't worry about missing a larger rectangle. We can search in each side separately. We also consider the rectangle whose height is the height of the shortest bar, the one that traverses the whole histogram, because it's possible for it to be the largest one. Even if it has the smallest height, but its width can make it the most interesting rectangle. In code, we create a recursive function that takes as parameters the array of heights, but also low and high, the boundaries of the part of the histogram we're searching in right now. At the beginning, we search in the whole histogram, so low and high will be initialized to the index of the first and the last bar. The first base case is when the actual part is empty, when low exceeds right. We just return 0, we have no rectangle. Second base case, when we have only one bar, when low is equal to high. In that case, we just return the height of that bar. Else, we have the recursive case. We start by calculating the position of the shortest bar in the actual part. For that, we calculate the smallest height in the actual part, between low and high inclusive, then we search for its index, in the actual part again. Now that we have it, we recursively search for the greatest area in the left and right sides. For the left part, we put posmin minus 1 as the right boundary, and for the right part, we put posmin plus 1 as the left boundary. And for that short but wide rectangle, its height is the minimum height, we calculated before, and its width is the whole part we're searching in, high minus low plus 1. So we return the maximum between from left, from right, and min h times high minus low plus 1. This one represents the area of the short but wide rectangle. We also need a non-recursive function to call this one. The initial values of low and high are 0 and n minus 1, the index of the first and last bar respectively. For the time complexity, in the best case, the shortest bar is always in the middle, so in recursive cases, we divide the input size by 2. We have n for searching for the min and 2 times t of n by 2 for recursive calls. We got t of n is equal to 2 times t of n divided by 2 plus n. By using the master method, this recurrence relation gives O of n log n time complexity. But in the worst case, the shortest bar is always the first or the last bar. For example, when it's the first one, from the left the input size becomes 0, we get t of 0, but from the right the input size becomes n minus 1, we get t of n minus 1. Plus n to search for the minimum, we get t of n is equal to t of n minus 1 plus n. And if we keep replacing, this recurrence relation gives O of n squared time complexity, same as the previous solution. It's like we did nothing. What's slowing down the process is finding the minimum. Its cost is n, to search for the minimum in the range we're searching for. But we can optimize this. By using a segment tree for example, we can reduce the cost of searching for the minimum in a range to log n. The recurrence relation becomes t of n is equal to t of n minus 1 plus log n. We get O of n log n. Plus n to build the segment tree, we get an O of n log n time complexity, better than O of n squared. But we still have two solutions to discover. The strategy we used in our first solution is that, for each bar, we search for the next shorter bar from the left, the next shorter bar from the right, and we calculate the area of the rectangle. But always traversing bars again to search resulted in an O of n squared time complexity. What if we can traverse the histogram only once to find the next shorter bar of each bar? Yes, it's possible, by using a stack. We can maintain a stack in an increasing order. For example, we have 2, 4, 7, 8, then we want to insert 5, but it wouldn't be increasing anymore, so we keep popping until we find a smaller element. And we push, it remains increasing. Then again, we have 6, 9, 10, 12, then to insert 8, we pop 12, we pop 10, we pop 9, and we insert. And so on. And we can use this principle for our problem. We work with heights. We maintain a stack, and to find the next shorter bar from the left of the actual bar, we keep popping until the top of the stack becomes shorter. After it, we also push the actual bar for the next iterations. Let me show you how it works with our example. We can add 2 bars of height minus 1 at extremities to avoid having an empty stack. Minus 1 to be sure that they will be shorter than any bar. At the beginning, the stack contains the bar 0, and we start from bar 1. The top of the stack is shorter, we already found the next shorter, it's at index 0. And we push the actual bar. Next index, the top of the stack is higher, we pop. Now it's smaller, the index of the next shorter is 0, and we push the actual bar. Next bar, top of the stack is shorter, we already found. Next shorter is the bar at index 2, and we push the actual one. Next bar, same thing, top of the stack is shorter. Next bar, same thing. Next bar, we pop once and we find it. Next bar, we have to pop all of them except the last one, because they are all higher. Next bar, the top of the stack is already shorter, its index is 7. Next bar, already shorter. And it continues like this for the whole histogram. Now we got the index of next shorter bar from the left of each bar, but we still need the one from the right, so we can apply the same process but from the right. The stack now initially contains the rightmost bar, the one we added from there, whose the height is minus 1. First bar from the right, the top is already shorter, and we push. Next bar, we pop once and we find the index, we also push. Next bar, already shorter, we write and we push. Next bar, same thing, we write and we push. Next bar, same thing. Next bar, same thing. Next bar, we pop twice, we write and we push. Next bar, we pop once, we write and we push. Next bar, we pop thrice, we write and we push. And the process continues like that. Now for each bar, we have the index of the next shorter bar from the left, the index of the next shorter bar from the right. We can calculate the largest rectangle that passes from the actual bar. For example, for this one, next shorter bar from the left is 0, from the right it's 7, so we get this rectangle. To get the largest one in the whole histogram, we traverse largest rectangle of each bar while keeping track of the global largest one, as we did in the first solution, but we don't need to search again here. And we've been able to solve the problem by traversing the histogram only thrice instead of n times, which will reduce our time complexity to O of n. In code, we first add those two bars of height -1 at extremities. Then, we create an array from left, where from left of I represents the index of the next shorter bar from the left of the bar I. We also create a stack that initially contains the first bar, the one we added. Now for each bar except once at extremities, we keep popping while the bar on top of the stack is higher or as high as the actual bar. We write, while heights of stack of -1 greater than or equal to heights of I, we pop. Stack of -1 represents the top element. After the loop, the next shorter bar from the left is on top of the stack. We assign it to from left of I. We also push the index of the actual bar, I. We finished filling from left, we will do the same thing from the right. We create from right, we initialize the stack by putting the last bar only, and we start. Now we traverse bars, but in the reverse order. Remember that we start from the right and we move. Same logic for what's inside the loop, but we assign to from right of I now. After having both arrays filled, we can start working. We initialize max area to 0, then for each bar, we check if we replace max area. Max area becomes the maximum between its actual value and the area of the rectangle of the actual bar. The height of the actual bar is height of I, and the width is from right of I minus from left of I minus 1. Minus 1 because the next shorter bars are not included in the rectangle, we don't count their width. So, the area is height of I times from right of I minus from left of I minus 1. After the loop, we return max area. For the time complexity, we have n to add those bars and n to create from left. And now for the loop, it's true that we have a nested while loop, where the total number of iterations won't exceed n, because each bar is pushed and popped only once, and we have n bars, so the cost is n. Same logic for the process from right, and we add n to search for max area. We get an O of n time complexity. And for the space complexity, we have n for heights, n for the stack, n for from left, and n for from right. We get an O of n space complexity. In this solution, we traverse the histogram thrice, but we have a solution where we traverse it only once. Let's talk about it. Okay, imagine that we have this bar as a first bar. We can still expand it from the right because we didn't find a shorter one. The next bar is this one. We can still expand them both. We found nothing that stops them. Third bar, same thing. Fourth bar, same thing. We can still expand them all because the heights are increasing. And we're putting them in a stack, by the way. But for example, the next bar is this one. This bar will let the previous 3 bars stop expanding because it's shorter than them. In other words, all bars that are taller than it in the stack. And because now we know where these bars stop, we can calculate their largest rectangle. The actual bar is at index 4, so they stop at index 3. For this bar, here is the rectangle. For the next one in the stack, here is the rectangle. And for the next one, here is the rectangle. We stop popping because the top of the stack is shorter, so it can still expand. You can see that what we're doing is that we're pushing our bars onto a stack, then when we find the next shorter bar from the right, we know where they stop. We calculate the rectangle. Now we push this bar and we continue. This bar is higher, we have nothing to pop, we directly push it. But for this one, it's shorter. So we pop this one and we calculate the rectangle. The top is still taller, we pop and we calculate the rectangle. But wait, with this bar, the largest rectangle that we can make is not this one, it's this one. The reason behind this wrong result is that the index of a bar is not necessarily from where its largest rectangle starts. In reality, its largest rectangle starts from where the last popped bar that iteration starts. For example, for this one, remember that we popped 3 bars, this one was the last one. It means that the largest rectangle starts from here. This is why when we push a bar, we keep the same height, but as index, we put the index where the rectangle of the last popped bar starts. Let's work with a greater example, the one we've been working with in this video. We can add those 2 bars of height -1 at extremities to avoid having an empty stack. First bar, the bar on top is shorter, we directly put it on the stack. Next bar, the bar on top of the stack is taller, so we found the end of its rectangle, it's I-1. The top of the stack is not smaller anymore, we stop popping. But now, when we push this bar, as height we put 2, but as index we put the index of the last popped bar, which is 1. Let's continue. 4 is taller, we just push with its index because we didn't pop anything. Next bar, same thing. Next bar, same thing. Next bar, we need to pop. And we found the end of this bar, here is its rectangle. And when we push 6, as index we put 5. Next bar, we need to pop. Here is the largest rectangle of the popped bar. Its beginning is the index we pushed and its end is I-1. We can calculate the rectangle and see if it replaces. Top is still higher, we pop. Top is still higher, we pop. Top is still higher, we pop. You can see that for each popped bar, we can easily find its largest rectangle. Top is not higher anymore, we stop. And the starting index of the last popped node is 1, so we put an index of 1 when pushing the actual bar. The reason behind it is that, from the left, our bar can extend until the index 1. From the right, we don't know yet. Next bar, higher, we directly push. Next bar, same thing. And the process continues like this until the end. After finishing, we found that the largest rectangle is this one. We return its area. And we've been able to solve the problem by traversing the histogram only once. In code, we start by adding those bars at extremities. We create max area, we create a stack, and we start traversing bars. The stack initially contains the first bar, the one that we added, and you can see that now we're storing both the index and the height. In the previous solution, we stored the index only because we could calculate the height from the heights array, but this time, the pushed index is not necessarily the one where the bar is in the histogram, so we store both. And this time, we need to traverse the bar at the right extremity to empty the stack, to calculate rectangles of bars that are still in the stack. So I start from 1 and goes until the last bar. At each bar I, we need a variable start that indicates from where the largest rectangle of the bar I starts. Remember that it's the starting index of the last bar we popped. But we didn't start popping yet, so we set it to I. Now we start popping. While the bar at the top of the stack is higher or as high as the bar I, we pop. We put the index and the height in 2 variables. Remember that we need to calculate the largest rectangle of the popped bar. Its height is the pushed height, its start index is the pushed index, and its end index is I-1. So its width is I-1 minus top index plus 1, which is I minus top index. We check if it replaces max area. Max area becomes max between its actual value and top height times I minus top index. And we're searching for the start index of the last popped bar, so start receives top index. After the loop, start now holds the start index of the last popped bar and the height of the actual bar is height of I. We push start height of I. And after the outer loop, we return max area. That's it. For the time complexity, once again, the inner while loop will do at most n iterations in total because each bar is pushed and popped only once. We got an O of n time complexity. And for the space complexity, O of n because of the stack and height array. We've reached the end of this video. In this one, we've seen different solutions to this problem. I hope that you understood them all. And that was the last problem of this course. Congratulations for finishing this course. I hope that you learned a lot of new things from it and will be able to apply them in other situations. To learn even more, you can check the other courses I made, like the 50 popular coding interview problems course. Check the links below. Also, please tell me what you thought about this course, if it's good, if it's bad, what should be improved, etc. See you in another occasion.